Day 1 of 365 had to start with big O notation because everything else in the track depends on it. Before arrays, trees, graphs, or system design trade-offs, I need one language for talking about performance. The useful shift today was treating big O as a growth model, not a speed label. It does not tell me how fast code feels on one machine. It tells me how the work grows as input grows, and that is a much better way to reason about algorithms. The first big lesson was that exact timing can be misleading. A small script may run instantly on a laptop even if the algorithm is weak. That does not mean the approach scales. Big O fixes that by asking a better question. If I grow the input from 100 items to 10 million, what happens to the amount of work? That question matters much more than a stopwatch when I want to compare two solutions to the same problem. The second useful shift was understanding the three common bounds clearly. Big O is the upper bound. It tells me how bad the growth can get. Omega is the lower bound. It tells me the minimum amount of growth I should expect. Theta is the tight bound, which means the algorithm really grows at that rate from both sides. In interview talk, Big O gets used most often, but theta becomes useful when I want to say the algorithm truly must do that amount of work. A simple example makes that clearer. If I scan an array to find the maximum value, I have to look at every element. I cannot know the answer without checking the full input. That means the algorithm is not only O, n. It is also omega, n, which makes it theta, n. That precision matters because it separates an avoidable cost from a cost that is fundamental to the problem. Another big lesson was how to read complexity from structure. One loop over n items usually suggests linear growth. Nested loops over the same data often suggest quadratic growth. Repeatedly cutting the search space in half suggests logarithmic growth. Divide and conquer work often lands at n log n. That mental model is not the whole subject, but it is the first practical tool I want on day one because it changes how I read code immediately. That also explains why asymptotic analysis matters outside interviews. When a code path slows down in production, the hidden problem is often inside the algorithmic growth. Maybe each request scans too much data. Maybe a nested loop is sitting on a hot path. Maybe the system is doing linear work for every request when the traffic pattern really demands something closer to logarithmic or constant time access. Growth rate becomes a real engineering concern once scale enters the picture. Another useful shift was realizing that Big O is not about worshiping the smallest notation at all costs. Constant factors, memory trade-offs, readability, and constraints still matter. But Big O gives me the frame to know when a cost is likely to dominate. If I see O, n squared, work on large input, I should be suspicious. If I can move a search from O, n, to O, log n, I should ask whether the extra structure is worth it. That is the kind of judgment the notation helps build. The first day also set up the rest of the track well, because Big O creates a habit of asking what operation dominates. Is the expensive part the loop, the recursion, the search, the sort, or the repeated scan? Once that habit becomes automatic, later DSA topics become easier to understand. Arrays are not just arrays. Hash maps are not just key value stores. Trees are not just nodes and pointers. They are all ways of changing the growth of common operations. Another important piece was resisting the urge to memorize notation as pure vocabulary. O, omega, and theta only become useful when they help explain a real piece of code. That is why I want every future topic in the track to tie back to growth. If I study prefix sums, binary search, heaps, or dynamic programming, I want to ask what runtime they improve and what cost they introduce in return. So my main takeaway from day one was that Big O is the performance lens for everything that follows. Ask how the work grows, ask which operation dominates, and ask whether the algorithm can avoid touching all of its input. If those questions become habitual, the rest of the DSA journey gets much easier to reason about. That is why starting with Big O was the right call. It makes every later topic more concrete from the very beginning.